Okay, picture this for a second. You are an engineer from 100 years ago, and you've been tasked with building a massive suspension bridge. You've done all your complex calculations, you've got a number, but to actually go out and cut the steel, you need an angle. Now today, you just pull out your smartphone, right? But back then, you literally had to go backward from a number to an angle using this massive, thick book of printed numbers. So, welcome to our explainer on this incredibly fascinating mathematical mystery, how to reverse engineer trigonometry without a modern calculator.
So here's our game plan for today. We'll start with the reverse math process, then move on to reading between the lines, followed by a two-answer plot twist, some special rules for small angles, and we'll wrap it all up with a big mathematical picture. All right, let's jump right into section 1, the reverse math process.
To really grasp this central mystery, we have to look at the tools of the time. Today, if you want to go backward from a ratio to an angle, you literally just press the inverse sine button on your calculator. Boom, instant answer. But historically, to reverse that process, you had to perform some serious manual detective work using printed logarithmic tables. It wasn't just a button press, you know? It was more like tracking down a suspect. Because these old tables were printed as logarithms to make those massive calculations a bit easier to handle, you kind of had to think in 3 distinct layers. First, you have to find the logarithm itself. That's layer 1. Layer 2 requires you to figure out what trigonometric value that logarithm actually represents. And finally, layer 3 is where you track down the actual angle. It's literally a 3-step puzzle just to get one single number.
Moving right along to section 2, reading between the lines.
Think of a logarithmic table basically like a dictionary, but what happens when the exact word you're looking for just isn't in there? Let's say our target value is 9.92657. If you scan through the tables, that exact number is totally missing. It falls right into the gap between the logarithm for 32 degrees and 24 minutes and 32 degrees and 25 minutes.
To solve this, historical mathematicians use this brilliant primary detective tool called interpolation. I know, it sounds like a big academic word, but simply put, interpolation is just finding something that lies between two things we already know. We know for sure our target angle is somewhere on the line between our two known table values. The table gives us the boundaries, but we have to estimate exactly where that unknown angle lives. We basically start at the lower value and figure out exactly how far up the line we need to travel.
And to measure that distance, we need the tabular difference. This is just the total gap between our two known table entries. Let's say the full gap between the two logs in our table is 14 units, but our target value is only 6 units above the lower boundary. Well, by dividing 6 by 14, we figure out we need to go about 42.9% of the way toward the next angle. It's just incredibly precise manual estimation.
But here is where you really have to pay close attention. Once you find that tiny correction value, what do you do with it? Do you add it to your starting angle, or do you subtract it?
It helps to think of it kind of like a thermometer. With the sine function, as the angle goes up, the sine value goes up. They move in the exact same direction. So, easy enough. You add the correction. But cosine behaves in the exact opposite way. As a cosine angle gets closer to 90 degrees, its value drops down to 0. Because they move in opposite directions, if your desired cosine logarithm is larger than the table value, you actually need a smaller angle. You have to subtract it.
Okay, this brings us to section 3, the two-answer plot twist.
So you've done the math, you've interpolated, and you found your angle. Let's say you figured out that the sine of your angle is 0.5, which means your angle is 30 degrees. Case closed, right? Actually, scratch that. You are totally wrong. Because in trigonometry, one clue can point to two completely different suspects. The angle is 30 degrees, but it's also 150 degrees.
To understand why this happens, we have to think about the all-important quadrant sine chart. Because trigonometric functions represent coordinates on a repeating unit circle, values appear more than once. Sine is the vertical coordinate, right? So it hits the positive 0.5 mark on the way up in quadrant 1, and it hits it again on the way down in quadrant 2. This concept is basically the ultimate cheat sheet that tells you exactly where your secondary answers can hide. So, the absolutely crucial point here is knowing how to find that second angle. If your sine is positive, your second answer is just 180 degrees minus your first angle. If you're dealing with cosine, it's 360 degrees minus your angle. And for tangent, because a negative divided by a negative equals a positive, you'll find your second answer sitting directly across the circle in quadrant 3, which is 180 degrees plus your angle.
Now, older math books, they love to throw these obscure functions at you, like secant or versine. But seriously, don't let them trick you. These are literally just clever mathematical disguises for our main suspects. Secant is just 1 over cosine. Versine is just 1 minus cosine. Once you peel off the disguise, you just turn them right back into a normal sine or cosine problem and use the exact same table techniques we just talked about.
Which leads us to Section 4, small angles and special rules. So what happens when we push this entire system to the extreme? If an old book gives you a logarithmic sine of -10, when you convert that out of logarithms, you get an incredibly tiny fraction. We're talking 0 point followed by 10 zeros and a 1. For practical engineering calculations, the resulting angle is essentially 0 degrees.
And this brings us to a really beautiful piece of math called the small angle approximation. When an angle is incredibly tiny, and as long as it's measured in radians, the sine of the angle is roughly equal to the angle itself. The sine of 0.01 is practically just 0.01. It's such a fundamental, elegant concept that actually forms the absolute bedrock of calculus later on.
But because the standard tables measure in degrees and minutes, ordinary interpolation completely breaks down when angles are smaller than 3 degrees. The math just changes way too rapidly. So historical engineers had to zoom in. They broke one single degree down into 3,600 arc seconds. And to keep things perfectly accurate, the books provided special correction values called S and T. If the normal table is like a rough tape measure, these S and T tables are a microscope, a really fine ruler allowing mathematicians to get exact answers for these microscopic angles.
And finally, Section 5, the big mathematical picture.
Let's zoom way out and look at the whole manual process we've uncovered today. Step 1, you take your clue and find the nearest table value. Step 2, you calculate the tabular difference and interpolate to find your exact angular correction. Step 3, you assemble your basic angle. And Step 4, you check the sine chart to find your second angle hidden elsewhere on the unit circle. It is a brilliant, entirely manual algorithm.
But here's the real kicker. What we've really been talking about this entire time is the inverse function, reversing the process from y back to theta. When you press that inverse sine button on a modern calculator, it is doing the exact same mathematical logic that an engineer back in 1910 did with a printed book. The core mathematics literally didn't change at all. Only the tool we used to process it got a whole lot faster.
Understanding how to confidently move backward from an output to an input is one of the single most critical skills in advanced mathematics. It's the engine behind differential equations, physics, and modern engineering. So I'll leave you with this thought. Now that you've seen the raw, manual mechanics of the inverse function exposed, how are you going to use this foundational idea to solve complex problems in your own work?